Hi everyone, I'm actually Will from MapR. I'm on the product team, so I deal with Stream. We have a product called MapR Streams and streaming technology. So what I'm going to talk to you guys about today is this concept that we often talk about with customers called streaming system of record. I'm going to talk about what that means. I'll tell you a little bit about MapR Stream because it's a good way to talk about this other concept that I want to talk to you about, which is versioning a real-time data pipeline, which can be very challenging, especially when you're populating downstream databases. And then we'll wrap up. Rupal's here with me from StreamSets. She has a demo of the StreamSets product with MapR demonstrating this concept of versioning a real-time data pipeline. So we'll do that in the last 10 minutes of the talk. So starting off, streaming system of record. What does this mean? So for those of you that have forgotten or just synchronizing terms, system of record, it's the storage that's the authoritative data source for any given element. Usually we talk about system of record with databases, so the new thing here is talking about it with streams. So before we get to streaming system of record, just one thing to talk about. Lots of data pipelines look like this. There's stuff producing events, it's going into a topic, that topic is going into some kind of processing, that processing is loading up the database, we're going to more processing, nothing new here. But raise your hand, for those of you that operate Kafka, if you're doing this today. This being taking data out of your queue and putting it into long-term storage like HDFS or something like that. Most of you, right? And the reason for this can be a couple-fold. So one reason you want to do this is because you want to do batch analytics on this. You want to do Hive queries or something like that. It's a good reason to do it. But the main reason I hear that people do this pattern is because with Kafka, you can't store events in there forever, right? So what you end up doing is piping into long-term storage, because once you touch that data in the first step of processing, you might break it, because that processing is code you wrote, code has bugs, you may change your mind later, you may bring a new application on that starts to process that data, and you want everything from the beginning. So you pipe it into long-term storage so that you always have access to all the data since you first start coming in. So that's why you do it. And that kind of makes sense, but it gets really messy when you actually want to do that thing, which is bring up a new app or change an app, reprocess all that old data. And it gets messy because now you have to figure out how to work out all of these arrows. So the first problem is, how do you get data from here into that app if all that app knows how to do so far is talk to streams? So it's, in the case of water, you want to move this hose over here, but it's a different fitting, so you have to work out how to get everything lined up. But worse than that, data isn't water. Actually, one drop is different than another drop, so you have to make sure that you have a way to figure out how to not duplicate the processing across what was in long-term storage, what was in your queue, and what was in both, since this is call it a year ago, or from time 0 to about an hour ago, 10 minutes, however often you have the connector coming up and running, to 3 days ago, or whatever your time to live is, until now. So how do you manage sucking in data from both of those? So that gets pretty hard. So what I would propose, first of all, is to go to a streaming system of persistence, which is getting rid of that long-term storage and just storing everything directly in your event queues. Now you're thinking to yourself, well, that's never going to work. It's not going to work because we've heard 2 talks so far about how you have to worry about rebalancing all your partitions, what happens when a partition fills to the end of a disk. You have to worry about all these things, the reasons why you have TTLs on your queues and you spill over in the first place. For now, just take my word for it that this is possible. I'll tell you how later. So now that we've gone through system of record, now we assume that a world exists where you can save all of the data in your stream. Now you can go one step further and get to a system of record. So to understand how this would work, let's take a simple case where the data going through your stream is transaction-based data, And here we're going to take a DMV example. So the transaction data going through, for simplicity, there's just 4 events going through. So the first event is me, I get registered with the city, and then there's some metadata associated with this transaction. So who put it in, what time it went in. Then a guy named Brad, I did this talk with a guy named Brad before. So Brad lives in Atlanta, etc. So all of these are changes to whatever the eventual DMV database is. So if you were to look at applying each one of these changes one by one to the resulting data set, what you would see is you process number 1, and you get a driver's license ID, city points, then Brad gets in there, and then Brad drives too fast, he gets pulled over, and he gets some points on his license, so his record changes, and then I move and my record changes. So now you see, some people refer to this as the duality of tables and streams, but you see how these things can kind of relate to each other. So now that we've seen this, you may ask yourself, what do I need a database for at all now? Can't I just do it all in the stream? Well, a stream can't be a replacement for your database. A database isn't really a replacement for your database. There are all sorts of databases out there. So there's key value, there's document, there's search engine, time index, geo, yada, yada, yada. So really the way to think about this is that you use this streaming system of record as a way to tame all of the different databases you have, because each one of them is tailored for a given read pattern or type of data or something like that. So now the concept is all of your transactions go first into a queue, and then anything that goes downstream of this is just a materialized view of that stream. So system of record is the stream, the databases are materialized view. And what that means is if you start day 1 with the key value database and you want to load everything into a document database later, that's okay. You bring up your document database, you inhale from the stream, and now you have a document database with all that same data. Search index, same way, time index, the same way. That's the power of having the system of record here. So in case you aren't convinced yet, you can look at both of those things and try to decide which one actually makes a better system of record. Well, the simplest question that I can think to ask in deciding that is which of these can be used to reconstruct the other. It's pretty obvious to see that if you look at all of these transactions, you can always reconstruct the state of the database, but you can never go the other way around. You never know how something got to be the way it was. So that's where we get into the other benefits of having this stream to your system of record. So one benefit is auditing. So asking yourself, how did something get to be the way it is? Lineage, who did this? Since we have all this extra metadata about when stuff happened, who did it, we can use that to do lineage type queries. You can get a full history. And of course, the integrity is there because by nature, streams are a immutable log. So you can be sure that as you're reading these things, they haven't been tampered with because they're immutable. So how do you actually do this? Well, number 1, you need a way to infinitely persist events. 2, you need a way to query that persistent stream. And 3, it's kind of a nice to have, but you need an integrated security model across all those services. So there's actually a lot more content on this pattern. There's a company that's doing it today called Liaison Technologies. In the slides that are going out along with this talk, you can click that and learn more about how they're actually using this. They're actually building a healthcare database as a service. So where do you get all these? You get them from MapR. So let's talk a little bit about that. So first off, MapR streams. So MapR streams is the thing that I wanted to talk to most tonight. So MapR streams is a streaming system. It's a pub/sub event streaming system. It is Kafka API compatible, which means Kafka apps can work transparently on top of MapR streams. So that's the consumers, the producers, any monitoring tool we might talk about are going to work on top of this because it implements the Kafka.net API. It does some pretty cool stuff though. Let me go through some of the interesting things that it does. So number 1 is it can be this persistent system of record. And I added a slide to explain how it can do this because we talked a lot about it tonight. So a lot of people that operate Kafka systems worry about how partitions get mapped to brokers and how they move around and things like that. The approach we took with this is an approach we call partitionless. So it turns out things get a lot easier in balancing the load of writes across the cluster if you don't actually pin any partition to any given node. So the way it works is each topic partition is actually a linked list of partitionlets, and those partitionlets can exist across any of the nodes. So as a producer starts writing, it's going to be writing to this head partitionlet. It's going to keep writing. When it hits about 4 gigabytes, it's going to cut it, and a new partitionlet's going to get open on some other node, and it's going to get open on another node based on load on the cluster right now. That's going to write to that one, and so on and so forth. So because of this, you no longer have to worry about any of these things of monitoring your nodes to see which partitions are where, or figuring out what partitions are about to fill up the disk and things like that. This is the fundamental thing that allows you to do this streaming system of record, because if you were going to store all these things anyway, you had to provision a Hadoop cluster big enough to store all these events. All you have to do here is provision the stream cluster to be that same size, and everything will stay in place, because like a Hadoop cluster, everything will get namespaced. Other things that we do, full global replication. So a couple of cool things we do about global replication. One is the metadata gets replicated with the data. So the metadata in this case is the consumer, or is the offset of that message. Meaning there are globally unique offsets for all messages in here. So if you start consuming from one cluster and you lose connection to that cluster and you go to one of its replicas in another cluster, the offsets are all going to be the same. You can pick up right where you get lost. In addition to that, as you've been committing cursors, those cursor commits are going to get replicated across too. So you can forget who you are, start consuming from another cluster, and that cluster already knows you because it got your consumer commits from the replica, and it'll go right where you left off. The other cool thing we do is loop detection and avoiding. So we make sure that if you can set up where every city replicates in a ring, we will make sure that we'll replicate around that ring, but cut it before you get your own messages so you don't worry about any loops. So that's some of the cool things we do for that. Multi-tenancy is the last thing that I'll mention. So rather than having a flat namespace of topics, we have a concept of streams, where a stream is a namespace of topics. So if you have multiple tenants or multiple applications or multiple users, however you want to do it, you can create a stream for each one of those. You can have 1 billion streams in the system if you want. Each one is a total namespace of topics, meaning you can give everyone, and everyone can have a topic named transactions if they want, and that's fine. And you can put a security policy around that, that's unique replication, etc. This is part of the converged data platform, so we also have a file system and database all in one system. And the reason I show the full-on architecture diagram is because this is the basis for the next concept that I'll talk about, which is how you version a real-time data pipeline. So now, so far we've talked about how to get all of your input data persisted directly in the stream it came into. That's pretty interesting. And one of the reasons you would want to do that is to version your app. But there's so many other problems that come when you actually try to version your app. So one of the problems comes when you're actually still in development on your app. So when you're in development on your app, probably you've got a test harness set up where you deploy your app. Jenkins is going to provision some infrastructure for you. You'll load in some test data. The test data will go through, populate some output data. You look at it, say yay or nay, and iterate and go. So the way that looks is you deploy your app, you deploy some topics for that version of the app, you deploy a database, you deploy some path to your cluster. You find your bugs, you deploy a new app, and the process continues. But because you're sharing all of these systems for each of your versions, you have to version each one of these. So you have events 2, events 3, because we learned earlier you can't really delete topics in Kafka. You do the same for the database, you do the same for your cluster. So eventually you've just got all of these systems full of dead topics, dead tables, etc. So that's kind of hard. But the harder thing happens when your app's actually in production. Because when your app's actually in production, versioning it means worrying about the output data. So the equation is simple. Input data plus your app logic equals your output data. And the output data is whether you put it in a stream, whether you put it in a database table, whether you load it to a log or something like that. So the hard part is, if you deploy a new version of your app, what happens to all the downstream tables that app is populating based on that data? So to illustrate this point, let's just do a little math example. So you have an input stream of data, it's just numbers. You have an app that's called calculate mean for you, which means it takes 3 numbers, calculates the mean, and puts it in a stream and a table. Excuse me. So this app's going, more numbers come in, those numbers calculated in the mean there, everything's fine until you get in one morning and your boss tells you, you're an idiot, you're not supposed to be calculating mean, you're supposed to be calculating median. Well, okay, you go and you fix the app, you deploy the app, more stuff comes in, and now you've got an output table with some mean, some median, you've got an output stream with some mean, some median. So how do you fix this problem? Well, you can worry about versioning everything, so every time data goes to the app, you kind of version to it, and you only trust one version to another. That gets kind of messy. Alternatively, you can use this construct that we have an app called volumes. So with volumes, what you end up doing is you create a volume for your app. So calculate mean 3 app, calculate mean 3 volume. There's a stream and a table in that volume. Stuff's coming in. And just like before, you calculate mean, you put this stuff in the table and the stream. Again, you get in the morning, your boss tells you you're an idiot. You deploy a new version called calculate mean in 3. But this time, instead of putting it in the same table, the same output stream, you create an entirely new volume. So in this new volume, you have a stream, still has the same name as an output table, still has the same value. But in this alternate universe, you've gone back to the beginning of the stream and you've reprocessed everything and everything ends up correct. So basically what you've done is you've gone into a time machine and deployed the app that you meant to at the time that you meant to, which was when your data first came in.
Yeah, basically downstream for the rest of the apps, usually it's not a single app. Let's say that this is like easy out, and there's probably an aggregation pipeline handles. So even if you go and integration this means that your downstream application exposes the whole data.
Right.
You have this graph management somewhere. So basically what I'm doing is essentially I'm doing a statement where I'm saying the data is back from X to C. Afterwards, expectation that then every downstream have to actually go and fix the data.
Right.
How do you handle it?
So the question is, it's not always just as simple as data getting loaded into a database. There are actually downstream apps, so how do you get your downstream apps to take this into account? So actually when Rupal does the demo in just a minute, it'll show one way of doing it, which is to actually kick off downstream pipelines to reset and reprocess from 0. And you can do that iteratively as you go on. So how this would actually look in an environment would be, so you have your stuff coming in, you have your app, this is like your calculate mean app with its volume, and you've got downstream systems. For simplicity, I'm assuming one downstream system, but it can be multiple downstream systems reading this database. So assume it's you're loading an operational table and it's running your website. So you found your bug, you redeploy app B. Now app B is going to need to warm up because it's got to scroll back in time and it's got to start reprocessing everything from the beginning. So it's going to warm up, it's going to start loading these topics, start loading this database. And meanwhile, while it's doing that, app A is still going in the background because you have 2 volumes with 2 different output data sets running in essentially 2 universes. And A is still the one powering your website until you decide that B is fully warmed up, it's ready, it's right. Now you just move the pointer. Another way of doing this would be you're running experiments. So you run this with B, C comes online, it has a small variant. Now you have 3 different tables populated from 3 different input pipelines with 3 different pieces of logic. Why not load balance here and do some A/B testing on it? You can do this with 1, 2, 3, 30, 50. however many you want, because each one of these is an independent data set. So that's how we actually operationalize this. And now Rupal's going to show up and do a demo of this concept with stream sets data pipeline. While she sets up, are there any more questions?
So the actually not the Kafka API is part of the interface. Is it that you emulate Kafka API for ingestion and users, or do you actually run Kafka alongside with the internet stream store?
So the question was, at what level do we implement the API? Is it wire protocol?
Yeah,
or so what we do is we do it at the client side. So we implement all the Kafka.9 Java APIs and write them on top of our client so that we can take them to our server layer. So all you have to do is load R, Kafka jar on the class path, and we'll take over and handle everything.
All right, thank you. So what I'm going to do is just jump straight into the demonstration, and I'll explain as well what StreamSets does as a company as well. So what you're seeing right now here is what we call StreamSets Data Flow Performance Manager. And what this allows you to do is create data flows. So for example, I know the first two presentations that were done, you create your Kafka consumers, your Kafka producers, you write your Java code, create beans, and so on. So StreamSets makes it easy with respect to creating pipelines by just using a graphical interface for creating these different streams. You don't need to write code, you don't need to know how to write code. Any user, whether it's a developer or an analyst, a business user can just go ahead and create pipelines to get data, whether it's in the Hadoop cluster or external systems. So with Data Flow Performance Manager, let's consider an example of a retail organization. In a retail organization, you all get like various emails giving you promotions, coupons that come in mail. And how this is done behind the scenes is you get data coming from point of sale systems, which is combined with your online transactions, maybe transactions you do through mobile applications, or even your social media and your customer service interactions that you do. So all this is aggregated, you do analytics on top of it, and then you get all these nice coupons that come in. So in order to evaluate this entire data flow of getting data from all these different systems, cleansing that data, passing it onto analytical systems, you have various applications which are written by various teams. So Data Flow Performance Manager makes it easy to give you a visual chart of all of this, but it also gives you this real-time monitoring aspect of how data is flowing through. So whether it's for just one data flow, whether it's between just one point, like how much data is sitting in a Kafka topic, in a MapR stream topic as well, or just an end-to-end flow of how data is flowing in real time. Now, consider each of these data flows to be a StreamSets pipeline. So a pipeline is nothing but, say for example, I look at the clean shopper data. A pipeline is going to be taking data from MapR streams, for example, and pushing that data into the other MapR services components. So now, as Bill explained, what if an application is deployed with a particular scenario in mind, right? In my particular scenario, the clean shopper data, I'll go ahead and open this within our StreamSets data collector tool, which is the actual pipeline tool for creating pipelines, basically. So here, I have this in production where I wanted to filter out data where somebody's last name is test, just simple test. Production data generally might have a few records which have test data, but you don't want this to interfere with your analytics purpose. So I'm just writing the simple pipeline that's going to filter out this data where last name is test. All this goes on, it works fine, goes into production, but after a few weeks, there's a person who calls up customer service saying, the coupon he got in his mail didn't work online. So customer service logs a bug, comes back to the engineering team to see what happened. And the issue there was, this guy's name was Chris Test. So Test is actually a valid name. So I have to go ahead and update my application and make sure that the downstream systems, as the question was asked, will start taking the actual correct data. So how all this is happening behind the scenes in MapR is, I'll show you as follows. So this is, I've logged into my MapR cluster and let me go into, so I've already, just for the demo purpose, I've already mounted these different volumes, and all these volumes in MapR are related to the application name plus the version number. So just for simplicity's sake, I've just created 3 different volumes to reflect customer shopper data version 1 through version 3. So right now, if I want to query the data that is already being populated into the MapR system for MapRDB, let's go ahead and query that to let me make this slightly smaller so we can see. And if I do a count on the table called so I get about 26,000 records, and I have some test data as well, so let me query that to show what I get. And the row key that I have, say for example, I have one as test. So there's no record for test. The row key that I created is basically a combination of the first name and the last name. And I also have a record that is coming into my stream as Eric test, just for test purposes. That also got filtered out. Now what I'll do is go ahead and update the application to say, now what's going to happen is I'll update the application with the correct condition, which should be filter every record which has both first and last name as test. So what's going to happen here is, first let me do that. I'll just quickly validate this. And I'll go ahead and publish this pipeline into our data flow performance manager. Just commit message. So what I see here now, the application changed to version 2. And notice I didn't make any change on the downstream MapR related component saying, okay, push this data now to a different volume. It's going to be done automatically. So if before I run this particular version, I'll also show you in my table as well that I don't have any data for my version 2 volume. So if I do a count now for clean shopper data version 2, it's 0. So I'll now start up this job for version 2, going back to the Info Performance Manager. I'll just make sure the new version has been pushed. I see version 2 here. I'll just create a job to run this quickly. That's a job for shopper here. Version 2 is selected. And I'll run it in my development environment, data collectors. And I'll just go ahead and start this up. So, Data Flow Performance Manager just manages all the data pipelines. The actual running is going to be done within the data collector. So if I go back to pipelines to see which pipelines are running, let's see, detailed control pipelines, and I'll just filter so we only see the clean shopper data. So I can see both version 1 is running simultaneously with version 2. And there's no conflict here because the volume that it's writing into, the destination that it's writing into is entirely different. Query the table as well to see if data is trickling in. There it is. So slowly I'm getting those records. Let's see. Alright. Performing a little slowly because of the network, but once this data flows in, we should be able to query the HBase table on clean shopper data too, and see that Eric test should now be there as a record in the HBase table. And there you have it. So the newer version now has correct data with last name as test. And if we query this for test, we should still not have this record. So that's the easiest way to have pipeline versioning along with having your MapR data to be versioned directly on your MapR systems. Any questions?
Thanks for all your work.